I have told you that an important consideration for this paper will be to develop summary methods and regression procedures for the case where we have discrete outcomes. In this paper, we will consider one of the simplest cases of discrete outcomes, which is the 2x2 table. The 2x2 table is historically important, and many of the methods which we use for proportions or binary data have arisen for the 2x2 table in the context of epidemiology. We shall define several alternative measures of association, see how they compare, and apply them to a sample dataset. The analysis of 2x2 tables. This means that we are looking at two variables, each of which has two categories. The 2x2 table is historically important in epidemiology, although of course there is no need that the data which we shall consider should necessarily arise only from epidemiological studies. But historically we have considered the 2x2 table in epidemiology, where if we label the two variables as x and y, x denotes an exposure which can be categorized as present or absent, y denotes a disease which again can be categorized as present and absent, thus leading to my 2x2 table with 4 cells. Now of course there is no need why exposure should always be present or absent. It could, for example, be several levels which may or may not be ordered, and the same could hold for disease. We could even have one continuous and one categorical. However, in this paper I am going to first introduce some fundamental concepts. For the 2x2 table, understand these, and then we shall apply these and extend them to the case where we have more general and more complicated kinds of data. So to begin with, here is a motivating example. Along the rows here, I am looking at two groups who have been assigned either placebo or aspirin. Along the columns, I am looking in fact at 3 categories, which is fatal attack, non-fatal attack, and no attack. Now this is not per se a 2x2 table, it is in fact a 2x3 table, as myocardial infarction has 3 categories. But to begin with, I am going to reclassify the data as fatal attack and non-fatal or no attack, and thus get a 2x2 table. This data arises from the ongoing physician study and has been well studied by Agresti and others. Now the simple 2x2 table can be used to motivate several alternative kinds of distributions. The first is the joint distribution. So initially we have 4 categories and thus a multinomial distribution with 4 categories whose corresponding cell probabilities we can denote by pi ij, I equal to 1 and 2, j equal to 1 and 2. We can of course generalize this to the case where we are looking at 2 variables, one of which has I levels and the second has j levels. In this case, the joint distribution is completely specified by pi ij, I equal to 1 to I, j equal to 1 to capital J. And of course, summation over both I and j, pi ij will be equal to 1. The second distribution which we can define are the marginal distributions. So for example, we might be considered the marginal frequencies along the rows. So we could fix one of the rows and look at how the frequency breaks up along the columns. This is denoted by the 2 marginals pi I plus, which gives the distribution along the rows. So pi I plus is summation over j, pi ij, for I equal to 1 to I, and pi plus j is summation over I, pi ij, j equal to 1 to capital J. So we have two sets of marginal distributions corresponding to either the rows or the columns. We can use this to define the conditional distribution. So for example, pi of j given I is the probability that an individual falls in the classification j for the second variable given that the person is known to be in classification I for the first variable. Of course, pi of j given I is pi ij by pi I plus. In subsequent modules, we will see that it is important to know whether we are considering the marginal distribution of two variables or the conditional distribution when we perform statistical inference, and that both distributions may not necessarily lead to the same conclusion. Let me first consider a very simple problem, which is that of comparing two proportions from a 2 by 2 tables. So for example, for a clinical trial, I could be interested in comparing the distribution for those who have been given placebo and those who have been given an active medicine, in this case aspirin, and to see whether the probability of no attack is different for the two groups. Now this means that I am referring to the conditional distribution, that is conditional on the fact that someone has given placebo or someone has been given aspirin. But for simplicity of notation, I am going to use pi I for pi of one given I. The first and simplest measure which we can define is the risk difference given by pi 2 minus pi 1. So for example, the probability of a fatal attack given that somebody is on aspirin minus the probability of a fatal attack given that the person is on placebo. I could of course redefine my categories and consider the probability of a non-fatal attack given that someone is on aspirin minus the probability of a non-fatal attack given that the person is on placebo. It does not really measure when I am looking at statistical significance, but I need to be careful of how I have classified the data as binary when I try to interpret the conclusions in the context of the data. Now it is not always necessary for me to look at the difference. An alternative means of measuring the association is to look at the ratio of pi 2 and pi 1. So I define the risk ratio or the relative risk as pi 1 over pi 2. Again, I could just as well have defined it as pi 2 over pi 1. And it does not matter if I am interested in testing a hypothesis that there is no association or that the risk ratio is 1. However, when I construct the confidence interval, for example, I need to be mindful of whether I have used the ratio pi 1 over pi 2 or pi 2 over pi 1 in trying to interpret this in the context of the data. I am going to define another ratio which you may or may not have seen before. I can quantify the chance of occurrence of an event by using the probability of the event. For this paper, I am going to refer to the probability of the event as a risk. But there is an alternative means of measuring the chance of occurrence of an event using something called the odds. The odds has been denoted on this slide using omega. So omega equal to pi over 1 minus pi, where pi is the probability of occurrence of the event, is called the odds of the event. So for example, if pi is equal to half, then omega is 1. Or I can say that there is a 50-50 chance of the event occurring or not occurring. Of course, given omega, I can always recalculate pi as pi equal to omega over omega plus 1, and thus the two have a one-to-one relationship. However, we shall see later that there are some cases where it is more natural to consider omega rather than pi as our metric of interest. The parameter which I shall define is the odds ratio. So theta equal to omega 1 by omega 2, which by definition of omega is equal to pi 1 over 1 minus pi 1 by pi 2 over 1 minus pi 2, is the odds of the event occurring for category 1 divided by the odds of the event occurring for category 2. This is called the odds ratio. So for example, for my given example, I may consider the odds ratio for someone on aspirin having a fatal attack as compared to someone on placebo. Now again, if there is an association, I would expect that the odds for the two categories would be different, and hence the odds ratio would be away from 1. If there is no association, then the risk and hence the odds for the two categories are the same, and we would expect the odds ratio to be around 1. The odds ratio is also sometimes referred to as the cross product ratio, and the reason is that for the simplest case, for the 2 by 2 table, the odds ratio is given by theta equal to pi 11 by pi 12 by pi 21 by pi 22, which can be rewritten more simply as pi 11 pi 22 by pi 12 pi 21. So because this looks like a cross product, I sometimes call theta the cross product ratio. Now note that the sample estimate of theta is theta hat equal to n11 n22 by n12 n21, where nij denotes the cell frequency for category I and j. You should be able to satisfy yourself that this is indeed the maximum likelihood estimator of the odds ratio using the property of invariance of the maximum likelihood estimate. Now going back to the aspirin data example, I have recategorized the data set as a 2 by 2 table, and I can calculate my 3 measures of association for this data set. So it turns out that the risk difference is 0.0171 minus 0.0094, which is equal to 0.00077. The risk ratio is equal to 1.82, and the odds ratio is equal to 1.83. So it seems that both the risk ratio and the odds ratio indicate the same thing. They're almost similar. Now, is this an accident? Not necessarily, because we see that the odds ratio is related to the risk ratio by the equation given on this slide. So the odds ratio is equal to the relative risk into 1 minus pi 2 over 1 minus pi 1. So in what situation would the two be equal? Of course, if pi 1 is equal to pi 2, that is, there is no association at all, then the odds ratio and the relative risk are exactly identical. But there is also another situation where even though not exactly identical, they are almost identical. This happens when the events are very rare, so that pi 1 and pi 2 are very close to 0, and that 1 minus pi 1 and 1 minus pi 2 are equal to 1 for all practical considerations. In this case, the odds ratio is almost equal to the relative risk. Why is this important? Now, it turns out that there is something called a retrospective design, which is often used in epidemiology and of course can be used in any other field. Suppose, for example, we are looking at the association between lung cancer and smoking. Given that lung cancer is a very rare event, if we consider two categories of smokers and non-smokers, say, we would have to follow them up for a very long time to find the required numbers of lung cancer in the two groups. This may or may not be feasible. An alternative way is to sample a group of those with lung cancer and a group of those without. Now note, when we are looking at lung cancer and smoking, our natural interest is in trying to predict whether a smoker gets lung cancer. However, because of the way I have sampled, which is from fixing the number of lung cancer patients and then looking at the distribution of smoking in the two groups, using our conventional notations of x and y, I can say that it is possible to estimate the probabilities of probability x equal to I given y equal to j. that is, to estimate the conditional probability of X given Y, in this case, smoking given lung cancer. We can argue that it is more natural to try and predict the occurrence of lung cancer given smoking and not vice versa. It turns out that when we use such a retrospective design, it is not possible to estimate the risk ratio. However, the odds ratio has a very remarkable property, which is that the odds ratio is invariant to study design. This can be proved using simply the definition of the odds ratio and Bayes' theorem, which can relate the probability of A given B to the probability of B given A for any two events A and B. The implication of this is that we can estimate the odds ratio X given Y, and it will be equal to the odds ratio of Y given X. If we further have the information that the outcome which we have measured is a rare outcome, then we can use the odds ratio as an approximation for the risk ratio. This is one approximate means of estimating the risk ratio when we use a retrospective design. Let us come to the problem of estimation. Now, the risk difference is something you will have seen earlier in the context of trying to conduct a test of the difference of two proportions from two independent samples. So we know that in this case we have pi1 hat, pi2 hat as the corresponding sample proportions, and we know that this is unbiased for the population difference of proportions. For the odds ratio, using the invariance property of the maximum likelihood estimator, theta hat is equal to n11 n22 by n12 n21, where nij denotes the cell frequency for the cell ij. There is a corrected version of this which accounts for the fact that some of the cell frequencies could be very small, and in fact, of course, an observed frequency could be exactly equal to 0. This inflates each of the cell frequencies by the amount of 0.5. The corrected version is due to Yule. To perform inference, we need to have information on the standard error of the estimates. We already know that it is possible to estimate the population proportions, or as I have labeled them in this case, the risks, using standard asymptotic theory. To further get the standard error for the risk difference or the risk ratio or the odds ratio, we have to use something called the delta method. Now, the delta method says that if I have a statistic Tn such that root n of Tn minus theta tends in distribution to normal 0 sigma square, then for sufficiently well-behaved functions, whereby well-behaved I mean that there are restrictions on the second derivative of the function, it turns out that root n of gtn minus g theta will tend in distribution to normal with mean 0 and variance given by g dash theta whole square into sigma square. We can use this to get the standard errors of the risk ratio and the odds ratio. Now, it turns out that it is easier and preferable to do this for the log odds ratio rather than for the odds ratio. So, we would then test the hypothesis that the log odds ratio is 0, and this would be equivalent to testing the hypothesis that the odds ratio is equal to 1. The same holds for the risk ratio. When we consider the log odds ratio, because of the additivity property of logs, it turns out to be the difference of the logs of the numerator and the denominator, and we can again break this up into the log of the risk, so log of pi minus log of 1 minus pi. This leads to a lot of simplifications, and the expression for the standard error of the log odds ratio is as given on the last line of this slide. It is a symmetric expression and very easy to remember. So the standard error of log theta hat turns out to be 1 over n11 plus 1 over n12 plus 1 over n21 plus 1 over n22 whole to the power half, whereas before Nij denotes the frequency corresponding to category Ij. So it's the sum of reciprocals of the frequencies and the square root to get the standard error. We can use the same method to get the standard error for the log risk ratio. In this case, it is not as symmetric, but it is still easy to remember as well as to derive. We have assumed for the odds ratio that we were sampling from the two rows. A contingency table can arise in many ways, and one of the methods is multinomial sampling, where we are not necessarily sampling along each row, but sampling from the entire table. So we have a total sample size, say n, and each individual could belong to any of the I cross j tables of the cell. So in case of a 2 by 2 table, the individual could belong to any of the 4 cells of the table. So in this case, we are referring to joint distributions, and it is necessary to use the multivariate delta method to derive the standard error for the log odds ratio. It turns out that the same kind of symmetry holds in this situation, and the expression using the multivariate delta method is as given below on this slide. Having derived the standard error, we would now wish to perform inference. This is not difficult because we know that the moment we can write down the likelihood under some standard conditions which will hold for these very simple cases. We have 3 ready-made tests. The first is the Walls test. So for example, to test the hypothesis whether the odds ratio is 1, that is, there is no association between x and y, or equivalently to test the hypothesis that the log odds ratio is 0, the Walls test could be constructed using log of OR hat divided by the standard error of log of OR hat, and we know that under H0 this would be normally distributed with mean 0 and variance 1. This is just one of the tests which we could use, and 2 other likelihood based tests which are always available whenever we can write down a likelihood are the score test and the likelihood ratio test. In some situations the tests will be identical, but not necessarily so. If we fail to reject H0, then our next procedure would be to get the confidence intervals for the log odds ratio or the odds ratio, or similarly for the risk difference and the risk ratio. This can be done by inverting any of the previously mentioned tests. Another statistic which you have heard of before in the context of likelihood analysis of a contingency table is the very well-known Pearsonian chi-squared statistic, and it is in fact one reason why likelihood inference was very popular for contingency tables. We shall revisit the Pearsonian chi-squared statistic in a subsequent module. In this module, we have considered a very simple but historically very important motivation, which is the 2 by 2 table. The 2 by 2 table is one of the fundamental concepts of epidemiology and helps us to understand the concepts of association, which we can later extend to more general settings. We have defined several alternative measures, namely the risk difference, the risk ratio, the odds ratio. We have compared them and seen that they may perform differently and indicate different things in different situations. However, for the case when we are observing a rare outcome, they will generally give similar conclusions. We have also visited the delta method and seen how it can help us to perform inferences about these measures, and finally we have applied the methods to a sample dataset.